Hello everyone and welcome back to G Fun Facts Online. I am your host, and today we are going deep. We are stripping away the noise, skipping the long introductions, and diving straight into one of the most mind-bending developments in modern physics. We are talking about a state of matter that should exist. We are talking about a technology that breaks the intuitive rules of the universe. We are talking about time crystals. I want you to start by imagining something impossible. Picture a clock that ticks forever without a battery. Or better yet, imagine a bowl of gelatin. You tap this gelatin once with a spoon, and it starts to jiggle. In the world we live in, the classical world, friction would eventually stop that jiggling. The energy would dissipate, the gelatin would settle, and stillness would return. But imagine if that gelatin didn't stop. Imagine it jiggled for eternity, never slowing down, never stopping, and crucially, never heating up. It just keeps moving, locked in a cycle, forever. In our world, governed by the relentless second law of thermodynamics, that object is a fever dream. It sounds like perpetual motion pseudoscience. But in the strange landscape of quantum mechanics, this impossible object is real. It is called a time crystal. To understand why this is such a massive deal, and to understand where we stand today in early 2026 with this technology, we have to go back to the fundamental language of the universe: symmetry. Physics, at its core, is a game of symmetries. When physicists say symmetry, they don't just mean something looks the same in a mirror. They mean that if you change a condition, the laws of physics stay the same. For example, we have spatial translation symmetry. This means if you do an experiment in New York and then move the whole setup to Tokyo, the results are the same. The laws of physics don't care where you are. We also have time translation symmetry. If you run an experiment on Tuesday and repeat it exactly on Thursday, you get the same result. The laws of physics don't care when you are. But symmetries can break. This is how the universe creates order. Think about liquid water. It is perfectly symmetrical. Every drop looks like every other drop. It's uniform. But if you cool that water down to 0 degrees, that symmetry breaks. The atoms snap into a rigid, repeating lattice. We call it ice. The ice isn't uniform anymore. It has a specific pattern in space. We call this crystallization. It's spontaneous symmetry breaking. For centuries, we believed this only happened in space. We thought matter could form repeating patterns in space, like a diamond or a snowflake. But time was different. Time was a flowing river. You couldn't freeze time. You couldn't chop time into repeating crystal-like chunks. Or so we thought. In 2012, Frank Wilczek, a Nobel Prize winner and a titan of theoretical physics, asked a heretical question. He was teaching a class on ordinary crystals and realized the math for space and time in relativity is remarkably similar. He asked, if atoms can spontaneously organize themselves into repeating patterns in space, why can't they do the same in time? He published 2 papers proposing the time crystal. He suggested that a quantum system in its lowest energy state, its ground state, could effectively move in a repeating pattern. Now this is shocking. The ground state is supposed to be the state of rest. In classical physics, if something is moving, it has energy to lose. Eventually, friction takes that energy, and the thing stops moving. It reaches equilibrium. Wilczek was suggesting a system where motion was the state of rest, a system that moves without burning fuel. Naturally, the physics community pushed back. Hard. It sounded too much like a perpetual motion machine. In 2013 and 2014, rigorous mathematical proofs called no-go theorems were published. These theorems proved, definitively, that in a system at thermal equilibrium, you cannot create a time crystal. You cannot break time translation symmetry in a resting state. For a moment, the idea was dead. It was a beautiful mathematical ghost, banished by the laws of thermodynamics. But science is stubborn. A group of theorists, including researchers from Princeton and the Max Planck Institute, found a loophole. The no-go theorems only applied to systems in equilibrium, systems that had settled down. But what if you never let the system settle down? What if you kept poking it? They turned to a branch of physics called Floquet theory, which describes driven systems. They realized that if you took a quantum system and hit it with a laser pulse rhythmically, you could create a state of matter that broke the symmetry of the laser's time. This leads us to the defining signature of a time crystal: period doubling. Let me give you an analogy to explain how weird this is. Imagine you are pushing a child on a swing. You represent the driver, the laser pulse. You push the swing once every second. In a normal system, the child swings back and forth once every second. The response matches the drive. But in a discrete time crystal, you push every 1 second, but the child swings back and forth every 2 seconds. The system spontaneously locks onto a frequency that is different from the force driving it. It creates its own internal clock. It's like tapping a drum 100 times a minute, but only hearing a beat 50 times a minute. That missing beat is the evidence that the material has crystallized time. Now, you might ask, if we are hitting this thing with a laser constantly, Why doesn't it heat up and explode? Usually, adding energy to a quantum system causes it to thermalize. It turns into a hot, chaotic soup. The magic ingredient that saves the time crystal is called many-body localization, or MBL. MBL acts like a quantum straitjacket. The particles in the material are so disordered, and they interfere with each other so strongly that they get stuck. They cannot absorb the energy from the laser. They can't heat up. Instead, they just flip back and forth, forever, in a coherent quantum dance. They are isolated from the thermal chaos of the universe. So, the theory was solid. We just needed to build one. The race began in 2016 between two heavyweights, Christopher Monroe at the University of Maryland and Mikhail Lukin at Harvard. Monroe used trapped ions, ytterbium ions lined up in a magnetic field. Lukin used diamonds, specifically dirty diamonds filled with nitrogen vacancy centers. Both teams saw the same thing. They hit their materials with pulses, and the materials responded with that signature period doubling beat. They had created the first discrete time crystals. This was 2017. It was a massive breakthrough, but there was a catch. These crystals were small, and they didn't last long. Skeptics argued that maybe these were just transient effects, not a true phase of matter. To prove a time crystal is real, you need to show it persists. You need a quantum computer. That happened in November 2021. Google researchers, using the Sycamore quantum processor, simulated a time crystal on a chip with 20 qubits. They ran the experiment for thousands of cycles. They proved that this wasn't a fluke. It was a stable, robust phase of matter. The Google experiment was the gold standard. It confirmed that time crystals were real, stable, and distinct from any other form of matter we had ever seen. Since that breakthrough in 2021, we have entered what I call the golden age of time crystals. The progress from 2022 to where we are now in 2026 has been nothing short of explosive. Let's look at a few highlights. In 2022, researchers in Helsinki created time crystals out of helium-3 superfluid. These were special because they were continuous time crystals. They didn't even need the laser pulse to keep the beat. They formed spontaneously. They even managed to put two time crystals in the same beaker and watch them interact, exchanging particles. That was the first time crystal logic gate, the great-grandfather of a time crystal computer. Then, in February 2024, a team at TU Dortmund in Germany shattered the duration record. Before this, time crystals lasted milliseconds. The Dortmund team, using indium gallium arsenide, created a time crystal that remained stable for 40 minutes. 40 minutes! In the quantum world, where things happen in nanoseconds, 40 minutes is effectively an eternity. It proved these states could be incredibly robust. And perhaps the most visually stunning development came just last year, in late 2025, from the University of Colorado Boulder. They used liquid crystals, the same stuff in your phone screen, to create macroscopic time crystals. Under a microscope, these didn't look like abstract data points. They looked like swirling psychedelic tiger stripes, oscillating and breathing on their own. For the first time, we could actually see the heartbeat of a time crystals. So we know they exist. We can make them out of ions, diamonds, superfluids, and even liquid crystals. But why do we care? What can we do with them? This brings us to the Time-Tronic future. The biggest problem with quantum computers today is decoherence. Quantum information is fragile. A tiny fluctuation in temperature or a stray photon can wipe out a qubit's memory. Time crystals are defined by their stability. They resist change. Because the crystal creates a rigid pattern in time, it resists being rushed or slowed down. If you encode quantum information into that time crystal state, the crystal naturally protects it. It acts as a shield against the chaos of the outside world. This has led to the concept of Time-Tronics, proposed back in 2024. Instead of electronic circuits that manage the flow of electrons in space, we're building circuits that manage the flow of states in time. Imagine a computer where the components aren't wires, but precise moments in time. A time crystal could act as the master clock for a quantum processor, synchronizing the chaotic qubits with unshakable accuracy. They also make perfect sensors. Because they are so locked into their internal rhythm, any tiny change in gravity or magnetic fields that shifts that rhythm can be detected with incredible precision. As we wrap up, I want to leave you with a philosophical thought. The existence of time crystals forces us to reconsider the nature of time itself. We usually define time as the thing that allows change. But in a time crystal, change is a closed loop. It breaks the symmetry of time spontaneously. This suggests that time, like space, isn't just a background canvas. It is a physical variable. It can be structured, it can be broken, it can be crystallized. We live in a universe that is slowly dying. The ultimate fate of all classical matter is heat death, maximum entropy, zero motion, absolute stillness. But the time crystal offers a loophole. It is a rebellion against that stillness. It is a small pocket of order that refuses to settle down. refuses to stop dancing, and refuses to succumb to the thermal grayness of the universe. From Frank Wilczek's chalkboards to the quantum chips of Google and the labs of 2026, the time crystal is the matter that moves without energy. The clock is ticking, and this time, it looks like it will never stop. Thanks for listening.